LogPath, log data-based energy consumption analysis enabling electric vehicle path optimization. Electric vehicle path optimization is important due to the recharging time of the battery and the lack of infrastructure. Current electric vehicle path optimization algorithms focus on computational speed and lack accuracy. By leveraging log data from the EV's battery, more accurate parameter estimation can be done for the individual vehicle during a trip. The log data is comprised of a timestamp, the current, the voltage, and the vehicle speed. The log data can be used with traditional physics to create an energy consumption model of the vehicle and solve for the variable parameters of the trip. The free body diagram of the forces on a vehicle can be used to clearly obtain the equation for the total force as shown. From this, we can then compute the maximum range a vehicle can travel. These are the important parameters obtained from the force equations. From the drag force, the important variable parameter is the coefficient of aerodynamic drag. From the friction force, the coefficient of rolling resistance. The inertial force gives us the mass, and from the motor force there are two, both the auxiliary power consumption and engine efficiency. These parameters deal with the amount of charge that is available for use during a drive. The regeneration effect causes an increase in battery capacity, while the temperature causes a decrease when the temperature is at either extreme. To determine the variable parameters, we must first find these four states: vehicle stopped, constant velocity, constant acceleration, and energy regeneration within the log data. Using these equations and the previous states from the log data, we are able to solve mathematically for all of the parameters shown in the previous slides of using the total force equation. We used a modified Dijkstra's algorithm to compute the optimal path while including minimizing the charging needed at each station using these equations. To test our approach, we ran multiple different trips using estimated parameters from actual vehicles. As can be seen, the total travel time has a larger variance than current methods compute. This is seen here on this trip from San Diego to Boston, as we look at our total trip time, dependent upon summer versus winter, as well as a light load versus a heavy load. A similar pattern can be seen on the results from Seattle to Miami, as well as can be seen on the trip from San Francisco to New York. Even shorter long-distance trips, such as this one from Chicago to Las Vegas, it can be seen that the variance can be quite large. We tested this on multiple trips to make sure that the data follows the same trends, and as can be seen from this graph, they do. We varied the parameters in specific ways so that we could show that the parameters with the highest effect upon the traveling time are the temperature and mass. From our research, it can be seen that we can accurately predict the important parameters using the log data, and that using these parameters, we can obtain an improved and more accurate path dependent upon the trip that is being taken, as well as the different parameters used throughout the trip will have a massive effect on the travel time that you are experiencing.